We've already graphed equations of the form y equals a sine omega x and y equals a cosine omega x. Now what we're going to do is introduce a horizontal shift factor called the phase shift. For graphs, y equals a sine omega x minus phi equals a sine omega times the quantity x minus phi over omega, and y equals a cosine omega x minus phi equals a cosine omega times the quantity x minus phi over omega. Where omega is greater than 0, we have the following characteristics of the graph. The amplitude is equal to the absolute value of a. The period is 2 pi over omega, and the phase shift is phi over omega. So let's look at an example. So we're going to graph y equals 3 sine of 2x minus pi. Right off the bat, we should notice that the function is going to have an amplitude equal to the absolute value of 3, or 3. The period of the function is 2 pi over omega. Omega is the coefficient on x, so that's 2. 2 pi over 2 is pi. Finally, the phase shift is phi over omega. Phi is pi, and omega is 2, so the phase shift is pi over 2. Now what we're going to do is obtain a graph of the function. Remember, y equals sine of x has one full cycle as x varies from 0 to 2 pi. Therefore, this graph will have one full cycle as 2x minus pi varies from 0 to 2 pi. The way we're going to set this up then is we're going to find the starting point to the graph of y equals 3 times the sine of 2x minus pi by solving this little equation. And if we do that, we get 2x equals pi, so x equals pi over 2. So the graph, or one cycle, will start at pi over 2. One cycle is going to end when 2x equals 3 pi, or x equals 3 pi over 2. Now here's an interesting result. The graph starts at the value of the phase shift, and that will always be the case, and the graph ends at the value of the phase shift plus your period. Remember, the period is pi, so if I add 2 pi over 2 to both sides to the phase shift, I get 3 pi over 2. So that will always be the case. The graph of one cycle will begin at the phase shift and end at the phase shift plus the period. What we're going to do is take the interval from pi over 2 to 3 pi over 2 and divide it into fourths. So we're going to start our subintervals at pi over 2, or 2 pi over 4, and then to 3 pi over 4. Then from 3 pi over 4 to 4 pi over 4 pi. From 4 pi over 4 to 5 pi over 4. And then finally, from 5 pi over 4 to 6 pi over 4, or 3 pi over 2. Now what I do is I find the key points associated with the x-coordinates of the endpoints of my subintervals. So starting at pi over 2, because we're doing the sine function, we're going to start at pi over 2 comma 0. Then the sine function increases until it reaches x is 3 pi over 4, and the y-coordinate will be 3. Then I drop back down and I go to the x-intercept. Then at 5 pi over 4, I'm going to be at negative 3. And then finally at 3 pi over 2, I'm back to the x-intercept of at 3 pi over 2. I'm going to plot these 5 key points in the Cartesian plane and then trace in a smooth curve. When I do that, here are my points. Pi over 2 comma 0, 3 pi over 4 comma 3, pi comma 0, 5 pi over 4 comma negative 3, and finally 3 pi over 2 comma 0. We notice that the horizontal distance between the key x-coordinates of the key points is pi over 4 units. So if I extend this graph to the left, I'll have another point at pi over 4 comma negative 3. Continue going to the left, I'll have another point at the origin, 0, 0, and so on. I could also go in the direction to the right, so from 3 pi over 2, which is 6 pi over 4, I'll have another key point at 7 pi over 4 comma 3, etc. So if I do extend the graph, I obtain the following. So here we have a complete graph of y equals 3 times the sine of 2x minus pi.